We've all seen those breathtaking images of spiral galaxies like Andromeda, majestic, glowing swirls of billions of stars, so immense they capture our imaginations instantly. But if you look closely, just off to the side, nestled in the cosmic shadows, you'll notice something else: tiny, faint smudges of light that almost seem like afterthoughts in the grand cosmic portrait. These aren't camera glitches or distant stars. They are dwarf galaxies, the most common type of galaxy in the entire universe, yet also the most overlooked. For decades, astronomers regarded them as simple, quiet backdrops to the great galactic show next door. But what if these tiny cosmic neighbors are hiding secrets that could rewrite the story of the cosmos itself? Today, we're diving deep into the realm of these galactic runts, the unsung protagonists in one of modern astronomy's greatest ongoing mysteries. Though they may look insignificant, dwarf galaxies are anything but simple. In recent years, strange and unexpected discoveries have turned our understanding on its head. From dark matter behaving in bizarre ways to stars that shouldn't exist, these faint collections of stars have become the center of some of science's most heated debates. They challenge the very foundations of how galaxies form, how dark matter shapes the universe, and even whether our current cosmic models are fundamentally flawed. In this video, we'll uncover 25 of the most startling, mind-bending findings about these miniature galaxies, facts so strange they almost sound like science fiction. We'll explore why some dwarf galaxies appear to be missing dark matter entirely, how others host ancient stars that defy stellar evolution, and what their peculiar orbits might reveal about the invisible cosmic web that binds the universe together. Each discovery peels back another layer of mystery, inviting us to rethink not only the life cycle of galaxies but the very nature of reality. So get ready for a journey into the farthest reaches of space, to the smallest and most enigmatic corners of our universe, where even the faintest lights can hold the biggest surprises. Our first strange discovery strikes at the very heart of modern cosmology, presenting a puzzle so profound it's known simply as the missing dwarf problem. According to our most sophisticated supercomputer simulations of the universe, which are built upon the bedrock of the dark matter model, our Milky Way should be surrounded by a veritable swarm of satellite dwarf galaxies. We're talking about a predicted thousands of these tiny galactic companions, each nestled within its own small halo of dark matter. Yet, when we point our telescopes at the sky and count what's actually there, the number is staggeringly low. We've only confirmed a few dozen. This isn't a minor accounting error. It's a glaring discrepancy between theory and observation that forces us to question some of our most fundamental assumptions. To understand why this is such a big deal, we need to look at the role of dark matter. Think of dark matter as the invisible scaffolding of the cosmos. After the Big Bang, it clumped together first, forming vast structures called halos. Ordinary matter, the stuff that makes up stars and planets, was then gravitationally drawn into these halos, eventually condensing to form galaxies. The model predicts a cosmic hierarchy, giant halos for galaxies like the Milky Way and Andromeda, and a multitude of smaller satellite halos for dwarf galaxies. The simulations show a Milky Way looking like a queen bee at the center of a massive, buzzing hive of tiny galaxies, but the reality we observe is far more lonely. Where we expect a dense cloud of faint lights, we see only a sparse collection. So, where did all the missing dwarfs go? Scientists have been grappling with this for years, and the proposed solutions are as fascinating as the problem itself. One leading idea is that our understanding of galaxy formation is incomplete. Perhaps the conditions needed for stars to ignite within these small dark matter halos are far more specific than we thought. It's possible that the vast majority of these predicted halos are indeed out there, but they are dark, completely devoid of stars, making them invisible to our telescopes. They would be halos of pure dark matter, ghost galaxies that we can only infer indirectly through their gravitational influence. Another, more radical possibility is that our models of dark matter itself need a serious revision. The standard model uses what's called cold dark matter, which moves slowly and clumps together easily. But if dark matter is slightly warmer or more interactive with itself, it wouldn't clump as efficiently on small scales. This would naturally lead to far fewer small halos forming, bringing the simulations much closer in line with the sparse reality we observe. This single discrepancy, this lack of tiny galaxies, is therefore a powerful probe into the fundamental nature of the most dominant form of matter in the universe. It reminds us that even in the emptiness, in the places where we see almost nothing, the cosmos is still whispering profound secrets. If the missing dwarf problem left you wondering about the invisible architecture of the cosmos, our second discovery will make that invisible world feel terrifyingly real. We now journey to the most dark matter-dominated objects ever discovered in the entire universe, the dwarf spheroidal galaxies. Picture the faintest, most diffuse collections of stars you can possibly conceive, so sparse and dim that for decades they were mistaken for mere star clusters or even photographic defects. Galaxies like Draco and Ursa Minor, which orbit our Milky Way, appear as little more than wispy smears of light against the black velvet of space. They contain only a few million stars, a paltry number compared to the hundreds of billions in a galaxy like our own. Yet, despite their ghostly appearance, these cosmic wraiths hold a monstrous secret. They are not just made of dark matter, they are absolutely overwhelmed by it, with over 99% of their total mass being completely invisible. The method for uncovering this bizarre reality is as elegant as it is conclusive. Astronomers can't see the dark matter directly, so they instead measure its gravitational fist by observing how the few visible stars within these galaxies move. Using powerful telescopes, they track the velocities of individual stars as they orbit the galaxy's center. In a system dominated by normal matter, like our solar system, stars closer to the center orbit much faster than those on the outskirts, following predictable laws. But in dwarf spheroidals, something astonishing happens. The stars, whether they are near the center or far out in the galactic fringes, all move at roughly the same incredibly high speed. This can only mean one thing: the stars are tracing out the shape of a massive, unseen gravitational field, a vast and heavy sphere of dark matter that envelops the entire visible galaxy. The visible stars are just a few scattered lights embedded within an immense, invisible iceberg. This leads to a truly mind-bending conclusion about their composition. When astronomers calculate the mass required to produce those stellar velocities and compare it to the paltry amount of light emitted by the stars, the numbers are staggering. These faint, star-poor galaxies have mass-to-light ratios that are thousands of times greater than that of our Sun. In practical terms, this means that for every kilogram of material we can see, every star, every speck of cosmic dust, there are thousands of kilograms of dark matter pulling it along. They are the cosmic equivalent of a featherweight balloon possessing the gravitational heft of a mountain. This profound dominance is what makes them perfect natural laboratories for studying dark matter's fundamental properties, as the confusing effects of normal matter are almost entirely filtered out. The sheer strangeness of these objects forces us to confront a universe that is far weirder than it appears. We are looking at ghost galaxy structures where the visible component is essentially a minor contamination within an overwhelming sea of darkness. Their existence challenges our intuition about what a galaxy even is, suggesting that the defining characteristic of a cosmic structure may not be its stars, but the invisible halo that gives it form. This incredible dark matter dominance in the smallest galaxies provides a crucial clue to a much larger puzzle, hinting at a deep and fundamental connection between the scale of a galaxy and the nature of the dark matter that birthed it. Just when we thought we had a handle on the dark, dominant nature of dwarf galaxies, the cosmos decided to show us just how much we still have to learn. Enter the third and perhaps most visually baffling discovery, the ultra-diffuse galaxies, or UDG. Imagine finding a cosmic ghost ship, an object the size of a massive, fully rigged galleon, but built from nothing more than mist and whispers. That is the essence of a UDG. These galaxies, with unforgettable names like Dragonfly 44 and NGC 1052DF2, have the sheer physical dimensions of the Milky Way, spanning tens of thousands of light-years across. Yet they contain only 1% of its stars, sometimes even less. They are so sparse, so ethereally faint, that they were only discovered in large numbers recently because our telescopes simply weren't sensitive enough to see these vast, empty expanses for what they truly were. The existence of something so large yet so dim immediately spawned the failed galaxy theory. The idea is hauntingly beautiful. Perhaps these UDGs are the cosmic equivalents of a tree that never managed to sprout leaves. They assembled the same immense dark matter halo that a grand spiral galaxy would need, gathering a colossal amount of raw gas. But then, for some reason, the star-forming process just stalled. Maybe a nearby larger galaxy stripped away their gas, or perhaps their internal dynamics were so tranquil that the gas never condensed efficiently to ignite new stars. They are the celestial might-have-beens, frozen in a state of arrested development, forever preserving the faint, wispy echo of what could have been a brilliant galactic metropolis. But the plot, as it always does in this cosmic mystery, thickens dramatically. While many UDGs, like Dragonfly 44, do seem to be dominated by dark matter, just like the dwarf spheroidals we discussed earlier, a few spectacular outliers have turned that expectation completely on its head. The most famous rebel is NGC 1052DF2. When astronomers measured the motions of its star clusters, they were prepared to find the telltale signs of a hefty dark matter halo. Instead, they found something that sent a shockwave through the astrophysics community. The clusters were moving slowly, lazily, at speeds that could be entirely accounted for by the gravitational pull of the visible stars alone. There was no need for, and no evidence of, any significant amount of dark matter at all. This single observation creates a paradox of staggering proportions. It directly contradicts the previous discovery where we saw dwarf galaxies completely overwhelmed by dark matter. How can the same class of object, a dwarf galaxy, exist in two such radically different states? How can one be 99% dark matter while its cousin, of a similar size and stellar content, appears to have almost none? This isn't just a minor inconsistency, it's a fundamental challenge to our models of how all galaxies form. If dark matter is the essential scaffolding that draws in normal matter to build a galaxy, then how did NGC 1052DF2 manage to build itself on such a grand scale without that scaffolding? It's as if we found a skyscraper standing tall with no foundation, defying every known principle of engineering. This contradiction forces scientists to consider wild new possibilities, from dark matter being able to be stripped away in violent galactic interactions to the idea that our very definition of a galaxy might need to be rewritten to encompass these bewilderingly diverse objects. But if you thought ultra-diffuse galaxies were strange, wait until you hear about a type of dwarf that is born from pure chaos. Our fourth discovery takes us to the scene of a galactic train wreck, where colossal spirals slam into each other in one of the most violent events in the universe. From the magnificent debris of these collisions, something new and unexpected can emerge: tidal dwarf galaxies. For a long time, astronomers believed that the violent, messy process of a galactic collision could only produce temporary, short-lived clumps of stars that would quickly dissolve back into the void. The idea that a stable, long-lived galaxy could be forged in such a turbulent crucible was considered almost heretical. Yet, that is precisely what we are now finding. The formation process is a spectacular cosmic ballet of destruction and creation. When two large galaxies, each containing hundreds of billions of stars, swing too close to one another, their mutual gravitational pull becomes a destructive force. They don't simply bump into each other, they gravitationally shred one another, pulling out vast streams of gas, dust, and stars into long, luminous tidal tails that can stretch for hundreds of thousands of light years. It's within these colossal rivers of debris that the magic happens. Dense knots of gas within these tails can collapse under their own gravity, triggering intense bursts of star formation. If a knot is massive and dense enough, it can hold itself together gravitationally, becoming a self-contained, orbiting island of stars. A brand new tidal dwarf galaxy born from the ruins of its parents. This unique origin story gives these galaxies a very special and very telling chemical signature. Unlike primordial galaxies that formed from the pristine, hydrogen-rich gas of the early universe, tidal dwarfs are built from pre-processed material. They are made from the recycled guts of galaxies that have already lived long lives, where generations of stars have fused hydrogen and helium into heavier elements, what astronomers call metals. This means tidal dwarf galaxies should be born inherently rich in metals like oxygen, silicon, and iron. Furthermore, and this is the crucial part for the dark matter mystery, they are born in the galactic outskirts in the tidal tails. The dominant theory of dark matter suggests it forms large, diffuse halos. During a collision, the collisionless dark matter halos of the parent galaxies would simply pass through each other, while the collisional gas and stars get pulled out into the tails. Consequently, a galaxy forming in a tidal tail should be made almost exclusively from this ordinary matter, possessing little to no dark matter at all. This pristine nature makes tidal dwarfs exceptionally valuable cosmic experiments. They are the control group in our study of galaxy formation. By confirming that they are indeed lacking dark matter and are metal-rich, we can powerfully test our dark matter models. If we find a galaxy that looks and quacks like a tidal duck, meaning it's located in a tidal tail and has a high metal content, but still has the gravitational signature of a massive dark matter halo, then our understanding of dark matter's behavior would be in serious trouble. So far, observations are largely aligning with the predictions, strengthening the case for the standard model. But every confirmed tidal dwarf galaxy is another data point, another piece of evidence helping us untangle the complex roles that dark matter and violent interactions play in building the diverse family of galaxies we see today. They are living proof that from the greatest cosmic disasters can come entirely new worlds. Now, if you thought the ultra-diffuse galaxies were ghostly, prepare to meet a cosmic wraith that makes them seem almost substantial by comparison. Tucked away in the vast celestial sea orbiting our Milky Way is a tiny speck known as Segue 1. To the untrained eye, it would be utterly invisible. Even to astronomers, it appeared for years as little more than a faint, insignificant smudge, easily mistaken for a sparse and unremarkable star cluster. But this unassuming speck is a galactic David hiding a Goliath's heart, and it holds two profound secrets that make it one of the most tantalizing objects in the entire sky. The first secret is its sheer gravitational might. When researchers meticulously measured the velocities of Segue 1's handful of stars, they discovered they were whipping around at speeds that simply didn't match the paltry amount of starlight the galaxy emits. The calculations that followed revealed a truth that borders on the absurd. Segue 1 appears to contain several 100,000 times more mass than can be accounted for by its visible stars. This gives it the highest mass-to-light ratio of any known galaxy, making even the dark matter-dominated dwarf spheroidals we discussed earlier look almost ordinary. In essence, Segue 1 is less a collection of stars and more a colossal, invisible sphere of dark matter with a few lonely stars sprinkled throughout, like a handful of glitter tossed into a vat of tar. This extreme concentration makes it a prime candidate in the hunt for one of physics' holy grails, the direct detection of dark matter particles. This leads us to the second, equally astonishing secret locked within Segue 1's ancient stars. While its dark matter content is immense, its chemical content is almost zero. Spectroscopic analysis of its starlight reveals a stunning poverty of metals, the term astronomers use for any element heavier than hydrogen and helium. The stars in Segue 1 are among the most chemically primitive ever found anywhere in the universe. They are pristine relics, fossils from a time just after the Big Bang, composed almost exclusively of the primordial hydrogen and helium that filled the early cosmos. This means the galaxy itself must have formed its stars only once, in a single, brief burst, and then never again. The supernova from that first and only generation of stars would have been too weak to enrich the tiny galaxy with heavier elements, leaving later generations of stars no raw material to form from. Segue 1 is a stillborn galaxy, a cosmic time capsule frozen in its infancy. The combination of these two properties, an overwhelming dark matter halo and a population of pristine stars, makes Segue 1 a uniquely powerful laboratory. Its primitive stars act as a direct window into the universe's first stellar generation, allowing us to study the conditions that existed when the very first stars ignited. Furthermore, that incredibly dense core of dark matter offers a potentially unmatched opportunity. According to some theoretical models, when dark matter particles collide with one another in such a dense environment, they could annihilate each other, producing a faint but detectable shimmer of gamma-ray radiation. Astronomers have pointed the most sensitive space telescopes at Segue 1, searching for this telltale glow. While a definitive signal remains elusive, the very fact that we are looking highlights how this faintest of smudges in our sky could be the key to unraveling two of the greatest mysteries in science: the nature of the universe's first light and the identity of its dominant, invisible matter. Just when we think we have dwarf galaxies neatly categorized as simple, dark matter-dominated relics, the universe reveals another layer of defiance. Our sixth discovery shatters a long-held cosmic rule, proving that the very smallest galaxies can harbor the very largest of secrets. For decades, the narrative was clean and simple: supermassive black holes, those gravitational monsters weighing millions or even billions of times the mass of our Sun, were the exclusive trophies of grand spiral and elliptical galaxies. They were seen as the price of admission for being a major galactic player. Dwarf galaxies, by contrast, were thought to be too small, too quiet, and too primitive to host such colossal engines at their hearts. That comforting assumption was completely overturned by a tiny, unassuming galaxy named Hennies 210. This dwarf galaxy is a powerhouse of contradictions. While it is hundreds of times smaller than the Milky Way, it is a veritable stellar fireworks display, churning out new stars at a rate so ferocious it puts our own galaxy to shame. At its core, astronomers found a brilliant, compact source of radio waves and X-rays, a classic fingerprint of a feeding black hole. But this was no ordinary black hole. The data revealed it to be a genuinely supermassive object, roughly 1 million times the mass of our Sun, squatting right in the center of this tiny galaxy. The implications were staggering. It meant that a galaxy doesn't need to be enormous to grow an enormous black hole. The seeds of cosmic leviathans can be planted in the humblest of galactic soils. What makes Hennies 210 even more extraordinary is that its black hole isn't just a passive resident. It appears to be an active and creative force. Observations from the Hubble Space Telescope showed a luminous, hot gas jet stretching like a cosmic umbilical cord from the galactic center directly to a nearby stellar nursery. Unlike the destructive jets from larger black holes that can shut down star formation, this one seems to be doing the opposite. It is compressing the interstellar gas along its path, triggering the birth of a brilliant cluster of new stars. This paints a surprising new picture of black holes in the early universe, suggesting that the very first supermassive black holes may not have just been chaotic destroyers, but could have played a vital role in lighting up the cosmos by sparking the formation of the earliest galaxies. This discovery fundamentally changes our understanding of black hole origins. The presence of these million solar mass black holes in dwarf galaxies like Henne's 210 provides the strongest evidence yet for a theory known as the direct collapse model. The idea is that in the dense, chaotic conditions of the early universe, vast clouds of primordial gas could have collapsed directly into massive black hole seeds, bypassing the stage of being a regular star altogether. These seeds, weighing anywhere from 10,000 to 1,000,000 solar masses, would then have had a tremendous head start, growing over billions of years into the behemoths we see at the centers of galaxies today. The dwarf galaxies that host them are therefore not just miniature versions of their larger cousins. They are living fossils, pristine time capsules that have preserved these ancient seeds since the dawn of time. Finding these black holes in dwarfs is like finding the original acorns from which today's giant oak trees grew. They offer us a unique window into a period of cosmic history that is otherwise nearly impossible to observe directly. By studying the properties and populations of these black holes in nearby dwarfs, astronomers can effectively conduct a galactic archaeological dig, piecing together the conditions that existed when the first structures in the universe began to form. Every dwarf galaxy found to contain a central black hole is another crucial data point, helping us understand how these gravitational monsters first took root and how they co-evolved with their host galaxies over the eons. The small, it turns out, truly does hold the key to understanding the very large. And just as we're grappling with the bizarre contradictions within individual dwarf galaxies, another conflict emerges on a grander scale, a problem rooted not in what we see, but in what our simulations insist should be there. Welcome to the too big to fail problem, a paradox that pits the sheer predictive power of our best cosmic models against the stubborn reality of an apparently emptier sky. The name itself is a nod to the financial institutions deemed so large and integral that their collapse was unthinkable. In a cosmic parallel, the most massive dark matter subhalos predicted to orbit our Milky Way are so incredibly dense and gravitationally robust that, according to all our understanding of galaxy formation, they should have easily gathered gas and lit up with stars. They were, in essence, too massive to fail at becoming brilliant, noticeable dwarf galaxies. Yet, when we search the skies, these predicted titans are conspicuously absent. We simply don't see the bright, large satellite galaxies that the simulations so confidently generate. To grasp the depth of this problem, picture the Milky Way's dark matter halo not as a smooth sphere, but as a lumpy, hierarchical structure built from the merging of countless smaller halos over billions of years. Our most advanced computer models, which simulate the evolution of this cosmic dark matter web with exquisite detail, consistently show that a handful of the largest and most massive of these subhalos should have survived to the present day. Their immense gravitational wells are so deep that even the intense radiation from the early universe and the gravitational tug of war with the Milky Way shouldn't have prevented them from forming vast collections of stars. The simulation expects us to be orbited by several dwarf galaxies, each as bright and prominent as the small Magellanic Cloud, one of our brightest satellites. The reality, however, is a collection of dwarfs that are far fainter and less massive than predicted. It's as if our census of a major city predicted a dozen towering skyscrapers, but when we arrive, we find only a scattering of low-rise buildings. So, what happened to these cosmic behemoths? Why did they fail to form the brilliant galaxies we expect? Astrophysicists have been wrestling with this, and the proposed solutions take us into the complex interplay between dark and ordinary matter. One compelling line of thought points the finger at the tumultuous lives of the dwarfs themselves. Imagine one of these massive dark matter halos in the early universe. It successfully draws in a huge reservoir of gas, and the first generation of stars ignites. But these weren't gentle, sun-like stars. They were monstrous, short-lived behemoths that lived fast and died young in cataclysmic supernova explosions. In the confined space of a small galaxy, these supernovas could have created a powerful collective wind, effectively blowing the remaining star-forming gas right out of the shallow gravitational well. The galaxy, starved of its fuel, would have had its star formation snuffed out almost as soon as it began, leaving behind a dark matter halo that is indeed massive, but now filled with only a faint, ancient population of stars, a ghost of its predicted brilliance. Another, more radical possibility is that our assumptions about dark matter are, once again, too simplistic. The standard cold dark matter model treats these particles as essentially collisionless and non-interacting except through gravity. But what if dark matter has some additional, subtle properties? What if it can interact with itself through some unknown force, or even with ordinary matter in ways beyond mere gravity? These self-interactions could cause dark matter particles to scatter off one another within the dense core of a halo, effectively smoothing out the central density and making the gravitational well shallower. A shallower well would be far less effective at holding onto gas, making it easier for supernova winds to expel it and shut down star formation. In this scenario, the halos are still there and they are still massive, but their inner cores are less concentrated, leading to the formation of the faint, ultra-diffuse galaxies we do see, rather than the brilliant beacons we expected. This too-big-to-fail problem is more than just a technical discrepancy in a computer model. It's a powerful reminder that galaxy formation is a messy, non-linear process where feedback, the energy and momentum injected back into the system by stars and black holes, plays a decisive role. It suggests that the final appearance of a galaxy is not dictated by dark matter alone, but by an intricate dance between the invisible scaffolding and the violent, life-giving processes of the ordinary matter it contains. By studying the faint, ancient dwarfs we do find, we are essentially reading the cosmic history of this feedback, understanding how the first stars shaped the galaxies around them, and perhaps taking the first steps toward a more complete theory of the dark universe that surrounds us all. Now, let's journey away from the crowded galactic downtown and out into the cosmic countryside. While many dwarf galaxies are satellites to giants like the Milky Way or live in the crowded, violent environments of galaxy clusters, a significant number lead lives of quiet solitude. These are the isolated or field dwarf galaxies, adrift in the vast emptiness between major cosmic structures. And their very solitude has revealed something unexpected. When left to their own devices, these galactic hermits often lead much more active and orderly lives than their city-dwelling relatives. A perfect example is the graceful IC1613, a dwarf irregular galaxy that floats in the local void, free from the gravitational bullying of any larger neighbor. This isolation creates a perfect natural laboratory. For decades, astronomers assumed that all small galaxies were simple, quiet, and ancient, their star-forming days long behind them. But when we studied isolated dwarfs like IC1613, that stereotype shattered. Unlike the faint, spheroidal satellites of the Milky Way, which are largely devoid of gas and form no new stars, many field dwarfs are bustling with activity. They often retain vast reservoirs of pristine hydrogen gas, the raw fuel for star birth, and they use it. Observations show them actively forming new stars in a steady, ongoing process, leading to a mix of both ancient and brilliant young stellar populations. Their structures, often classified as irregular, are not the result of external damage but appear to be natural, dynamic shapes maintained by their internal processes. They are not disturbed, they are independent. The key to understanding this difference lies in the concept of galactic harassment. A dwarf galaxy orbiting a giant like the Milky Way doesn't have a peaceful life. Every time it swings close on its orbital path, it experiences immense tidal gravitational forces. These repeated tugs strip away its gas and drastically warp its structure, pulling stars away into long streams and effectively sterilizing the galaxy by robbing it of the material needed to make new stars. Cluster dwarfs face an even worse fate, bullied not just by one giant but by the combined gravitational field of hundreds of galaxies, along with the pressure from the superheated intra-cluster gas that scours away their cool hydrogen. It's a cosmic environment of relentless stress. An isolated dwarf galaxy, by contrast, is free from this turmoil. Floating in the tranquil emptiness of the field, it holds onto its gas reservoir indefinitely. This allows it to form stars at its own pace, governed by its own internal clock. Without violent external triggers, its star formation can be self-regulated, proceeding in a more gentle and continuous manner. This makes these galaxies exceptionally valuable for astronomers. When we study them, we are seeing a galaxy in its most pure, unaltered state. We can observe how star formation ignites and propagates through a cloud of gas under the influence of its own gravity, without having to untangle the complicating effects of a recent collision or a tidal stripping event. They are the control group of cosmology, showing us what a dwarf galaxy is naturally like when it's left alone to evolve in peace. This pristine quality also makes them ideal for testing our fundamental theories of dark matter. The rotation of a field dwarf's gas disk is thought to be a direct map of its dark matter halo's gravitational pull. Without the confounding gravitational shocks from nearby galaxies, the rotation curves we measure are clean and unambiguous. Any discrepancy between the observed rotation and the predicted distribution of dark matter can therefore be attributed to the properties of the dark matter itself or our understanding of galaxy formation, rather than to a messy recent interaction. In this way, the quietest, most solitary galaxies in the universe are speaking some of the clearest words about the invisible cosmos, teaching us that sometimes, to hear the deepest secrets of the universe, you have to listen to the silence. But to truly understand the life story of a dwarf galaxy, we sometimes need to look past its shape and size and directly into the chemical hearts of its stars. Every star is a cosmic chemist, and the elements it contains are a permanent record of the galactic environment in which it was born. This brings us to our ninth discovery, one written in the very atoms of these tiny galaxies, the strange and revealing chemistry of dwarf galaxy stars, which provides a history book written in a language entirely different from our own Milky Ways. When astronomers point their spectrographs at a star in our galaxy, the precise wavelengths of light absorbed by different elements in the star's atmosphere create a unique chemical fingerprint. For the vast majority of stars in the Milky Way's disk, this fingerprint shows a very specific and consistent pattern in the ratios of certain elements. In particular, the ratio of alpha elements like oxygen, magnesium, silicon, and calcium to iron remains remarkably constant for a wide range of stellar ages. These alpha elements are primarily forged in the short, violent lives of massive stars, which end their lives as core collapse supernova, scattering their enriched guts into space within just a few million years. Iron, on the other hand, has a different primary source. It takes a longer time to build up in a galaxy, as it's predominantly produced in type Ia supernova, which are the thermonuclear explosions of white dwarf stars that can take billions of years to occur. The steady ratio in the Milky Way tells a story of continuous and well-mixed chemical evolution, where star formation has been a constant, self-regulating process over eons, with different types of supernova contributing to the chemical soup at a steady pace. Now, read the chemical fingerprints of stars in many dwarf spheroidal galaxies, and you find a story that is dramatically different and far more abrupt. In galaxies like Sculptor or Fornax, the chemical pattern is not a steady line but a broken record. The most ancient stars in these dwarfs often show a high ratio of alpha elements to iron, similar to the oldest stars in the Milky Way. This indicates that the first burst of star formation in these small systems was indeed intense and prolific, producing a generation of massive stars that quickly enriched the galaxy with alpha elements. But then the story diverges. For stars that formed just a little bit later in the dwarf's history, the alpha-to-ion ratio plummets. This is the crucial clue. It tells us that after that first generation of massive stars exploded, there was a significant pause. During this quiet period, the core collapse supernova stopped, halting the production of new alpha elements. But the slower type Ia supernova kept ticking along, eventually detonating and flooding the galaxy with iron, thereby diluting the alpha-to-ion ratio for all subsequent generations of stars. This chemical signature paints a vivid and often tragic picture of a dwarf galaxy's life. It suggests a history of a bursty star formation, where activity is not continuous but happens in short, frenzied bursts separated by long periods of quiescence. The reason for this fits perfectly with what we know about their fragile nature. A dwarf galaxy has a very shallow gravitational well. When the first massive stars in a burst explode as supernova, the collective energy is so immense that it can easily blow most of the remaining star-forming gas right out of the galaxy. The galaxy is left gas-poor and unable to form new stars until some of this ejected gas can cool and fall back in, or until a fresh supply is acquired, a process that can take hundreds of millions of years. It's a cycle of boom and bust, of brilliant firestorms followed by cosmic ice ages, all recorded in the elemental abundances of its stellar population. This chemical contrast provides one of the most powerful pieces of evidence for the different evolutionary paths of large and small galaxies. The Milky Way, with its deep gravitational well, could withstand the fury of its own supernova. It held onto its gas, allowing for continuous cycling and mixing, resulting in a homogeneous chemical history. A dwarf galaxy with its weaker gravity could not. Its star formation history was inherently unstable, easily disrupted by its own internal feedback. So, by simply analyzing the light from a single star in a distant dwarf, astronomers can determine not just the star's age, but also read the grand narrative of its entire host galaxy, a story of dramatic beginnings, sudden interruptions, and a quiet, fading end, all from the unique chemical language spoken by its ancient suns. The universe has a way of warping our perception in the most literal sense imaginable, revealing its hidden architecture through the subtle bending of light itself. We've explored how the immense gravitational pull of dark matter in dwarf galaxies tugs at their stars. But what if that same gravity could reach out across cosmic distances and distort the very fabric of reality for other, far more distant objects? This brings us to our 10th astonishing discovery, the fact that even these faint, low-mass galaxies can act as gravitational lenses. It's a concept that sounds like it belongs exclusively to the domain of colossal galaxy clusters, whose titanic gravity can twist background galaxies into spectacular arcs and rings known as Einstein rings. The idea that a mere dwarf, a cosmic speck, could produce any measurable lensing effect seems almost preposterous. Yet, through the subtle phenomenon known as flexion, that is precisely what astronomers are now detecting. So how is this possible? The secret lies in moving beyond the classic, strong lensing that creates those beautiful, obvious arcs. Strong lensing requires a truly massive foreground object to warp spacetime so severely that it acts like a giant magnifying glass, creating multiple, distorted images of a single background galaxy. A dwarf galaxy simply doesn't have the sheer mass for that. Instead, its influence is far more delicate. It produces what is called weak gravitational lensing. In weak lensing, the background galaxies aren't torn into multiple images or dramatic arcs. They are just slightly, almost imperceptibly, distorted. Their shapes are sheared, stretched in a particular direction, and crucially, they undergo flexion, which is a subtle, higher-order bending. Imagine a faint, distant spiral galaxy. As its light passes through the gravitational field of a foreground dwarf galaxy, the dwarf's gravity doesn't just stretch the image uniformly. it imparts a slight curl or warp to the edges, a telltale signature of a complex gravitational field. It's the difference between gently pulling on a piece of taffy and giving it a slight, sophisticated twist. Detecting this effect is a monumental feat of observational precision. Astronomers must statistically analyze the shapes of thousands, even millions, of extremely faint background galaxies that lie behind the dwarf galaxy in our line of sight. They look for coherent, minute patterns of distortion that align around the dwarf's location. By meticulously measuring the precise amount of this shear and flexion, they can work backwards to map the total gravitational field responsible for it. Since the visible stars contribute almost no mass, this mapped field is a direct pixel-by-pixel chart of the dark matter distribution within the dwarf itself. It's a way of seeing the invisible halo by observing how it warps the light of everything behind it. This technique provides a powerful and independent check on the mass measurements we get from stellar velocities, and in some cases, it offers an even more detailed view of the dark matter's structure, probing its density and how it changes from the galactic center out to the faint edges. This ability to use dwarf galaxies as cosmic scales for dark matter is revolutionizing our understanding. For decades, the primary method for weighing dark matter in these systems was to watch how their stars move. But that method has its limitations, especially at the very outskirts of a galaxy where stars are few and far between. Weak lensing, however, works beautifully precisely in those outer regions, using the vast sea of distant background galaxies as probes. This gives us a much more complete picture of the dark matter halo's full extent and shape. Furthermore, it helps settle debates. For instance, when we encounter an ultra-diffuse galaxy that appears to have no dark matter based on its internal star motions, weak lensing provides a crucial second opinion. If lensing also shows no significant mass, the case for a truly dark matter-deficient galaxy becomes ironclad. Conversely, if lensing reveals a hidden halo, it would force a dramatic reinterpretation of the object's nature. In this way, these tiny galaxies, by bending the light of the ancient universe, have become some of our most precise tools for interrogating the dark side of the cosmos, proving that even the faintest objects can cast the most revealing shadows. Now, let's rewind the cosmic clock all the way back to the universe's infancy, to a time before galaxies as we know them even existed. Our 11th discovery pulls these tiny galaxies from their role as modern-day curiosities and casts them as the potential heroes, or at least the prime suspects, in one of the most important transformations in cosmic history, the epoch of reionization. For the first several hundred million years after the Big Bang, the universe was a vast, opaque fog. It was filled with a dense, neutral hydrogen gas that scattered light, preventing it from traveling freely across space. The cosmos was adrift in a formless gloom. Then something happened. Something began to blast this fog away, tearing electrons from the hydrogen atoms in a process called reionization, and transforming the universe into the brilliant, transparent expanse we see today. For decades, the question has remained, what was the source of this powerful, ionizing radiation that cleared the cosmic dawn? The leading suspects for this monumental task have always been the first luminous objects to form, the earliest stars and galaxies. But here's where dwarf galaxies enter the scene with a compelling claim to the title. The very first galaxies to ignite in the young universe were almost certainly dwarfs, small, fragile collections of stars and gas. And the first stars born within them weren't like our placid sun. They were colossal behemoths known as population 3 stars, dozens or even hundreds of times more massive than our own star. These stellar titans burned ferociously hot and bright, and they emitted a flood of high-energy ultraviolet photons, the exact type of radiation needed to rip electrons away from hydrogen atoms. Think of a single, massive dwarf galaxy in the early cosmos not as a gentle candle, but as a powerful ultraviolet blowtorch, punching ionized bubbles into the surrounding neutral hydrogen fog. This leads to a fierce and ongoing debate in cosmology. Were there enough of these small, faint dwarfs to do the job on a universal scale? The challenge is one of numbers versus power. The most massive early galaxies would have been far more potent individual sources of ionizing radiation, but they were also much rarer. The multitude of tiny, faint dwarf galaxies, however, would have been incredibly numerous, like a vast cosmic population of sparks. If there were enough of them, their collective, distributed effort could have been far more effective at permeating the entire cosmic medium and completing the reionization process. They wouldn't just create a few large, isolated bubbles. They would create a Swiss cheese-like structure throughout all of space, their bubbles eventually overlapping and merging until the entire cosmic fog had lifted. Observational evidence is beginning to tilt the scales, thanks to the incredible power of telescopes like the James Webb Space Telescope. Webb is now peering back to this critical era and finding exactly what the dwarf galaxy theory predicts: a universe teeming with tiny, faint blue smudges of light. The early cosmos appears to have been absolutely packed with small, star-forming dwarf galaxies. While we are still in the process of taking a full cosmic census from 13 billion years ago, the initial data suggests their numbers were indeed vast enough to have been the primary drivers of reionization. It appears increasingly likely that the monumental task of clearing the universe's primordial fog was not accomplished by a few brilliant giants, but by a countless army of faint dwarf galaxies, the unsung workhorses of the cosmic dawn, whose collective faint glow was enough to illuminate the entire universe for all that was to come. If you thought the universe had run out of ways to surprise us, consider a galaxy that seems to have been turned on its side. Our 12th discovery highlights one of the most structurally bizarre formations in the cosmos: dwarf galaxies with polar rings. Picture a fairly typical flattened dwarf galaxy, a frisbee of ancient stars spinning quietly in the void. Now imagine a second distinct ring of gas, dust, and young stars encircling it, but on a completely different plane orbiting around the galaxy's poles, perpendicular to the main disk. This creates a celestial structure that looks like a giant, spinning cosmic egg beater, a configuration so strange it defies our standard images of what a galaxy should be. To understand how peculiar this is, we can look at a famous, larger-scale cousin, Hoag's object. This stunning ring galaxy appears as a nearly perfect circle of brilliant blue young stars surrounding a central, spherical core of older, yellow stars with a stark, dark gap in between. It's a mesmerizing sight, but it's also a giant, a massive galaxy that showcases the phenomenon on a grand scale. The discovery of similar polar ring structures around much smaller dwarf galaxies, however, is even more startling. It demonstrates that this architectural oddity isn't reserved for cosmic giants. Even the smallest galactic systems can achieve these complex, multi-planar structures, suggesting that the physical processes behind them are both universal and potent. The existence of such a precise, perpendicular ring points directly to a violent history of galactic cannibalism. The most widely accepted theory is that this dwarf galaxy had a smaller, gas-rich companion, perhaps another tiny dwarf or a massive star cluster. Billions of years ago, this companion ventured too close and was violently torn apart by tidal forces. As it was shredded, its stellar component would have been scattered, but its diffuse gas, possessing angular momentum on a different plane, would have been captured by the larger dwarf's gravity. This captured gas then settled into a stable orbit perpendicular to the main galaxy's plane of rotation, slowly coalescing over eons to form new stars and create the brilliant, contrasting ring we see today. It's a fossilized record of a past merger, a cosmic meal that left a visible ring of debris. An alternative, equally fascinating formation method involves accretion from the cosmic web itself. Vast filaments of dark matter snake through the universe, and along these filaments flows a steady supply of pristine, cold hydrogen gas. If a dwarf galaxy happens to move through such a filament, and the gas in that filament has the right rotational properties, it could be funneled directly onto the galaxy, but from a polar direction. This accreted gas would then form a new disk of material that settles into this perpendicular orbit, building the polar ring from the raw, unprocessed material of intergalactic space, a slow and steady construction project spanning billions of years. Regardless of how it formed, a polar ring is an astronomer's dream come true because it acts as a natural gravitational probe. The stars and gas in the main galaxy orbit within its primary gravitational field. But the stars and gas in the polar ring are tracing orbits that take them far above and below the main disk, sampling the galaxy's gravitational potential in 3 dimensions. By carefully measuring the rotation speed of the ring, astronomers can map the shape of the entire dark matter halo that surrounds the dwarf galaxy. If the dark matter halo is spherical, the ring will rotate one way. If it's flattened, it will behave differently. This gives us a direct way to measure the invisible architecture that dictates the galaxy's form and destiny. These rare and beautiful galactic hybrids are therefore more than just curiosities. They are dynamic historical archives. The age and composition of the stars in the ring tell us when the accretion or merger event happened. The ring's stability or lack thereof reveals the dynamic history of the galaxy and the gravitational forces at play. Each polar ring dwarf is a unique experiment, a frozen moment in a long-term dynamical process, showing us that even the simplest-looking galaxies can have surprisingly complex and violent biographies, written in the perpendicular orbits of their stellar rings. As we continue our journey through the strange lives of dwarf galaxies, we arrive at a discovery that reveals a more tragic cosmic fate. While isolated dwarfs can lead active lives, many of their cousins near giant galaxies have had their stellar fire extinguished, entering a state astronomers call quenching. This is the process where a galaxy's star formation is shut down, leaving it a passive relic filled with aging, red stars and devoid of the vibrant blue light of newborn suns. The stark contrast between a bustling, star-forming dwarf and a quenched one is like the difference between a thriving, youthful city and a silent, ancient ruin. The mystery of why this happens so efficiently around galaxies like our own leads us into a realm of violent astrophysical forces that dictate life and death on a galactic scale. One of the most dramatic quenching mechanisms is a process known as ram pressure stripping. To visualize this, picture a dwarf galaxy orbiting through the halo of a massive galaxy like the Milky Way. This halo isn't a perfect vacuum. It's filled with a thin but incredibly hot and fast-moving plasma known as the intergalactic medium. Now, imagine the dwarf galaxy as a spaceship flying through this superheated fog. As it moves, it experiences a tremendous wind of particles, a cosmic headwind so powerful it acts like a pressure hose. The dwarf's own reservoir of cool, dense hydrogen gas, the very fuel for future stars, isn't held in place by a strong gravitational grip. The ram pressure of this intergalactic wind can simply blow this gas away, stripping it from the galaxy's grasp in a single, violent event. It's a celestial version of having the rug pulled out from under you, where a galaxy's future is literally snatched away by the environment it travels through. Sophisticated computer simulations illustrate this process with stunning and terrifying clarity. You can watch as a dwarf galaxy, rich with blue, star-forming gas clouds, plunges into the denser regions of a galaxy cluster. Almost immediately, a visible wake of stripped gas forms behind it, like smoke streaming from a speeding car. The galaxy's own gravity struggles to hold onto its fuel, but the external pressure is overwhelming. Within a relatively short cosmic timescale, the dwarf is left gas-poor and bleeding, its star formation rates plummeting to zero as its lifeblood is scoured away. This isn't a gentle fading. It's a rapid and violent death for a galaxy's creative potential, a fate that befalls countless satellites as they fall into the gravitational dominion of a larger host. But quenching doesn't always require such a dramatic confrontation. A slower, more insidious process called strangulation achieves the same end through a different kind of deprivation. In this scenario, the dwarf galaxy isn't necessarily stripped of the gas it already has. Instead, its supply lines are cut. Galaxies need a continuous inflow of fresh, pristine hydrogen from the cosmic web to sustain star formation over billions of years. Strangulation occurs when the gravitational pull of the massive host galaxy, or the pressure of the surrounding intergalactic medium, prevents this new gas from ever reaching the dwarf. The galaxy is left to survive only on its existing, finite reservoir. It's like a town whose well hasn't been poisoned, but whose connection to the river has been permanently dammed. It can continue to live for a while on its stored supplies, but its long-term future is doomed. The evidence for this gradual starvation is written in the stars themselves. A quenched dwarf galaxy that has been strangled will show a very specific history in its stellar populations. It will have a population of old stars, proving it was once actively forming stars, but it will completely lack any young blue stars. Its star formation history won't show a sharp, abrupt cutoff as in ram pressure stripping, but rather a long, slow decline as it used up its last remaining gas reserves. This gentle fade out is the hallmark of strangulation, a quiet suffocation that stands in contrast to the violent blasts of ram pressure. Both processes, however, highlight a fundamental truth about cosmic ecology: location is everything. A dwarf galaxy's destiny is not determined by its initial mass alone, but by its neighborhood and its interactions with the colossal structures that dominate the cosmic landscape. But what happens when a dwarf galaxy doesn't fade quietly or get shut down? What if, instead of a gentle simmer, its star-forming engines are thrown into overdrive, creating a frenzy of creation so intense it can be seen across the universe? This brings us to our 14th discovery, the blue compact dwarfs, the cosmic firecrackers of the galactic world. These are galaxies like Zwicky 18, which appear as tiny, brilliant blue jewels against the darkness of space. Their intense, azure hue isn't from a peaceful, mature stellar population. It's the unmistakable signature of a galaxy-wide conflagration, a starburst of epic proportions where stars are being born in a ferocious, almost violent frenzy. These are not the quiet, red and dead relics we've discussed. These are dwarf galaxies in the throes of a spectacular creative explosion. The sheer intensity of their light tells a story of stellar youth and power. The blue color comes from an overwhelming population of O and B-type stars. These are the rock stars of the stellar world, monumentally massive, ferociously hot, and incredibly luminous. They burn through their nuclear fuel in just a few million years, a mere blink in cosmic time, before ending their lives in spectacular supernova explosions. In a normal galaxy like our Milky Way, these stellar behemoths are rare, mixed in with countless older, cooler, yellow and red stars, but in a blue compact dwarf they are the main event. The galaxy is essentially one giant stellar nursery, a sprawling, brilliant region of star birth so concentrated that the entire galaxy lights up like a neon sign. This makes them some of the most luminous dwarf galaxies known, their brilliance belying their small physical size. Adding to their mystery is their surprisingly simple chemical composition. When astronomers analyze the light from blue compact dwarfs, they find them to be remarkably poor in metals, the elements heavier than hydrogen and helium. This is a profound clue. In our own galaxy, the interstellar gas has been enriched by generations of supernova, polluting it with carbon, oxygen, iron, and silicon. The low metal content in blue compact dwarfs suggests one of two fascinating scenarios. Either they are genuinely young galaxies, latecomers to the cosmic party that have only just begun to form their first stars, or they are ancient galaxies that have lived in a state of suspended animation, preserving their primordial gas in a pristine state for billions of years until something recently triggered this ferocious burst of activity. This second possibility is particularly intriguing. It paints a picture of a galaxy as a sleeping giant, a reservoir of potential that has remained untapped for eons before suddenly, dramatically awakening. So, what cosmic alarm clock could trigger such a spectacular awakening? The leading theories point to dramatic environmental changes. One potent trigger is a merger or a close gravitational encounter with another small galaxy or a massive gas cloud. Even a minor interaction can send powerful shock waves through a dwarf galaxy's fragile gas reservoir, compressing vast clouds and triggering a chain reaction of gravitational collapse that ignites star formation across the entire system. It's like shaking a snow globe. The gentle motion stirs up the contents into a furious, beautiful blizzard. Another possibility is the steady, gentle accretion of fresh, cold gas from the cosmic web. If a filament of this primordial fuel finally connects with a quiescent dwarf, the sudden influx of raw material can overwhelm the galaxy's equilibrium, plunging it into a starburst frenzy as it struggles to process the unexpected bounty. This incredible burst of activity, however, comes at a great cost. The very same massive stars that make these galaxies so brilliant are also their eventual undoing. Their powerful stellar winds and the cataclysmic shockwaves from their supernova explosions inject a tremendous amount of energy back into the galaxy. In a system with such a shallow gravitational well, this feedback is catastrophic. It can easily blow the remaining star-forming gas clear out of the galaxy, effectively shutting down the starburst as abruptly as it began. The blue compact dwarf may blaze with the intensity of 1,000 suns for a few tens of millions of years, but it's ultimately a short-lived, self-limiting phenomenon. The galaxy will eventually exhaust its fuel, the brilliant blue stars will die off, and it will fade into a much quieter, redder state, a ghost of its former brilliant self, its brief, spectacular blaze of glory, a testament to the violent and cyclical nature of star formation, even in the smallest corners of the cosmos. Just when you thought the individual quirks of dwarf galaxies couldn't get any stranger, the cosmos reveals a pattern on the grandest of scales, a pattern that shouldn't exist. For a long time, astronomers assumed that the dwarf galaxies orbiting giants like our Milky Way and the Andromeda Galaxy were like bees buzzing randomly around a hive scattered in a roughly spherical cloud. This is exactly what the standard cosmological model predicts. It tells us that galaxies grow by merging with and accreting hundreds of smaller halos of dark matter, which should arrive from all directions, resulting in a swarm of satellites with random, independent orbits. But when scientists finally mapped the precise three-dimensional positions and motions of these satellites, they were met with one of the most shocking sights in modern astronomy. The dwarfs weren't scattered randomly at all. They were arranged with startling precision into vast, thin, and coherently rotating disks. Around our own Milky Way, this structure is known as the vast polar structure. It's a gigantic, pancake-like plane that is perpendicular to our galaxy's own spiral disk, and a significant number of our satellite dwarfs, including the famous Large and Small Magellanic Clouds, are aligned within it. Even more strikingly, many of these satellites are not just sitting in this plane, they are moving together, flowing along like cars on a cosmic freeway. This isn't just a random alignment, it's a dynamically coherent structure, but the Milky Way's plane is just the beginning. Our neighboring Andromeda Galaxy exhibits an even more dramatic and pristine example, the Great Plain of Andromeda. This structure is even thinner and more vast, containing nearly half of Andromeda's known satellite galaxies, all rotating in the same direction within a single, breathtakingly flat plane. The existence of these structures creates a monumental problem for our standard model of cosmology. The model, known as lambda cold dark matter, is incredibly successful at explaining the universe on the largest scales, the cosmic web of filaments and voids. But it consistently fails to produce these thin, rotating planes of satellites in its most sophisticated simulations. When supercomputers simulate the formation of a Milky Way-like galaxy, the resulting satellite dwarfs are indeed scattered in a much puffier, more spherical distribution. They do not neatly arrange themselves into a single, thin, rotating disk. The simulations show a chaotic swarm. Reality shows an ordered, rotating sheet. This discrepancy is so severe that it has become one of the most persistent and significant challenges to our entire understanding of how structure forms in the universe. So, how do we explain this cosmic defiance? Scientists have been grappling with this for years, and the proposed solutions push the boundaries of physics. One compelling, yet controversial, idea involves the very fabric of the early universe. It suggests that these planes are not a recent phenomenon but are cosmic fossils. In the incredibly dense and hot environment just after the Big Bang, immense waves could have propagated through the primordial plasma density fluctuations on a colossal scale. As the universe expanded and cooled, these waves could have imprinted themselves as vast, thin sheets of dark matter. Dwarf galaxies would then have formed preferentially within these pre-existing sheets, inheriting their coordinated motion from that initial impulse. In this view, the planes of satellites are the dying echoes of the universe's first moments, a fossilized imprint of cosmic infancy that has survived for over 13 billion years. An alternative and perhaps more intuitive theory looks to a more recent and violent past. It's possible that these planes are the aftermath of a colossal galactic collision. If two sizable galaxies merged billions of years ago to form what we now see as the Milky Way or Andromeda, the tidal forces from that collision could have pulled out a vast disk of gas and smaller progenitor dwarfs. This material would have naturally settled into a rotating plane, and the dwarf galaxies within it would have preserved that shared motion ever since. Another related idea posits that many of these dwarfs weren't accreted individually but were born together as a group, a cluster of dwarf galaxies that fell into the Milky Way as a single unit. Their shared origin would explain their common motion, much like a flock of birds that continues to fly together even after entering a new valley. Each of these potential explanations carries profound implications. If the planes are primordial fossils, they could provide a unique window into the physics of the very early universe, revealing phenomena that are otherwise completely inaccessible. If they are the result of a major merger, it would force us to rethink the quiet evolutionary history we've assigned to our galaxy, suggesting a far more violent and dramatic past. The sheer persistence of this puzzle reminds us that the universe often saves its most confounding mysteries not in the exotic and distant, but in the seemingly mundane patterns right in our own cosmic backyard. These vast, thin planes of tiny galaxies are a silent, spinning rebuke to our simplest models, a coordinated dance of dwarfs that continues to challenge our deepest understanding of the cosmos. Yet another mystery brewing in the faint light of dwarf galaxies challenges our understanding of dark matter at its most fundamental level. This one is known as the cusp versus core problem, and while it sounds highly technical, its implications are staggering, potentially revealing that dark matter is not the simple, inert substance we have long assumed. According to the prevailing lambda cold dark matter model, the universe's most successful cosmological recipe, dark matter is cold and collisionless. This means the particles move slowly relative to light, and crucially, they pass right through each other and ordinary matter, interacting only via the force of gravity. Supercomputer simulations based on these properties consistently generate dark matter halos with a very specific internal architecture, a density that rises steeply and continuously toward the center, forming what is known as a cusp. Imagine a cosmic mountain with an incredibly steep, sharp peak at its center. This is the predicted dark matter cusp. However, when astronomers turn from simulated universes to real observational data from dwarf spheroidal galaxies, they find a glaring contradiction. Instead of stars whipping around at ever faster speeds as they orbit closer to the galactic center, the telltale gravitational signature of a dense cusp, their motions tell a different story. The stars, whether near the center or far out in the galactic fringe, move at roughly similar velocities. This observation points toward a gravitational field that is consistent with a core, a central region where the dark matter density is relatively constant, like a flat-topped plateau or a gently rounded hill rather than a sharp peak. It's the difference between poking a steep, pointed pin and a blunt, rounded pencil eraser. The gravitational effect on the stars is fundamentally different. This core-like structure appears to be a common feature in many of the faint dwarfs we observe, creating a persistent and troubling mismatch between theoretical prediction and hard empirical evidence. So, how could a dark matter cusp transform into a core? This is where the physics gets fascinating. One of the leading explanations involves a process driven by the most powerful engines in a galaxy, supernova. In the early, turbulent life of a dwarf galaxy, it would have undergone bursts of intense star formation. The most massive of these stars would have lived short, violent lives, ending as core collapse supernova. In a small galaxy with a shallow gravitational well, the collective energy from countless such explosions could have been enough to literally push the center of the galaxy. This isn't a movement of stars, but a shifting of the gravitational bedrock itself. The explosive feedback from these supernovae would have transferred energy and momentum to the ordinary matter, which in turn gravitationally interacted with the dark matter, dragging it outward and effectively eroding the steep central cusp into a shallower, constant density core. It's a compelling idea, suggesting that the ordinary matter, for all its relative scarcity, can literally sculpt the invisible dark matter that dominates it. But there exists a more radical and profound solution. What if the problem isn't with the behavior of the ordinary matter, but with the intrinsic nature of dark matter itself? The core cusp problem is a powerful motivator for physicists to explore beyond the standard model of perfectly collisionless dark matter. Perhaps dark matter particles can interact with each other through some force other than gravity, a self-interacting dark matter. In this scenario, when dark matter particles in the dense central cusp collide and scatter, they transport heat from the hotter outer regions to the cooler center. This process of thermal conduction would smooth out the dense peak, naturally transforming a cusp into a constant density core over billions of years. It's analogous to how a spoon stirring a cup of coffee eliminates steep temperature gradients, creating a uniform warmth throughout. If this is correct, then the observed cores in dwarf galaxies are not sculpted by stars, but are the inevitable result of dark matter's own hidden thermodynamics. The resolution to the cusp versus core debate is therefore critical. It represents a fork in the road for fundamental physics. If supernova feedback is the primary solution, it means our models of galaxy formation, while complex, are on the right track, and dark matter remains the simple, collisionless particle we've long suspected. But if future, more precise observations and simulations firmly rule out feedback as the sole explanation, the door swings open to a much richer and more complex dark sector. Self-interacting dark matter would not only solve the core cusp problem, but could also address other cosmological puzzles, such as the surprising absence of dark matter in certain ultra-diffuse galaxies and the exact number of satellite galaxies around the Milky Way. The seemingly arcane distribution of mass in the faintest and smallest galaxies is incredibly a direct probe into the particle physics of the universe's most dominant yet elusive substance. Moving from the grand architecture of dark matter to the intricate jewels contained within these tiny galaxies, we uncover another perplexing anomaly that challenges our understanding of how stellar systems are built. Some dwarf galaxies, seemingly against all odds, host globular clusters that defy expectations. Globular clusters are typically envisioned as ancient, dense spheres of hundreds of thousands of stars, all born in a single frantic burst. They are the senior citizens of the galaxy, and in large systems like the Milky Way, they orbit the galactic halo like a swarm of bees, their properties generally in sync with the host. But in certain dwarfs, this harmony breaks down in spectacular fashion. Consider the Fornax dwarf spheroidal galaxy, a faint satellite of the Milky Way. Fornax itself is a classic example of a quenched, dark matter-dominated relic with a sparse population of old stars. Yet, orbiting this faint smudge are not one but 5 brilliant globular clusters. This in itself is unusual, a galaxy with only a few million stars somehow managing to hold onto multiple such massive clusters. But the real surprise comes from analyzing these clusters in detail. They are not just survivors, they are surprisingly massive and, even more curiously, appear to be more metal-rich than the general stellar population of the Fornax galaxy itself. This presents a cosmic version of a child possessing a more valuable heirloom than its parent. How can the clusters be chemically enriched with heavier elements if the galaxy they belong to is largely primitive? One compelling theory paints a picture of galactic cannibalism on a miniature scale. It's possible that these aren't native-born clusters at all, but rather the surviving nuclei of even smaller galaxies that Fornax devoured in its distant past. In this scenario, a small, gas-rich dwarf galaxy would have been gravitationally shredded as it was pulled into Fornax. The diffuse outer stars of this victim would have been torn away and assimilated into Fornax's main body, diluting its overall metal content. But the dense, resilient core of that galaxy, its central star cluster or nucleus, could have survived the tidal disruption intact. This surviving nucleus would then continue to orbit as what we now classify as a globular cluster, but it would carry the chemical imprint of its original, now destroyed host galaxy. This would explain both its high mass and its curious metal-rich signature compared to the cannibal that now hosts it. It suggests that the faint dwarfs we see today might be the assembled remnants of an entire hierarchy of even smaller galactic building blocks, a cosmic matryoshka doll of galactic destruction. An alternative and equally fascinating explanation looks not to destruction, but to an unusually efficient mode of creation. Perhaps these massive clusters did form in situ, right within the Fornax dwarf, but under conditions unique to low-gravity environments. The physics of star formation in a dwarf galaxy is profoundly different from that in a spiral like the Milky Way. With a much shallower gravitational well and a lack of strong tidal forces, giant molecular clouds in a dwarf could have been more stable and less prone to being ripped apart. This stability might have allowed them to grow to enormous sizes and collapse monolithically, forming a single, incredibly dense and massive star cluster in one fell swoop. The intense burst of star formation within such a colossal cloud would have been spectacular, rapidly enriching the cluster with metals from the first supernova. Meanwhile, the rest of the dwarf galaxy, forming stars at a more sedate pace, would have retained a more primitive composition. The cluster, in this view, is not a foreign implant but a homegrown superstar, a testament to a uniquely potent and focused burst of creation that the dwarf galaxy itself could never replicate on a larger scale. The implications of this mystery reach far beyond a single dwarf galaxy. If the cannibalism theory is correct, it means that the process of hierarchical assembly, where large galaxies build up by consuming smaller ones, extends right down to the very smallest galactic scales. It provides a potential mechanism for how the faintest dwarfs we see today were themselves assembled. If, on the other hand, the in situ formation model holds, it reveals that the efficiency of star and cluster formation is not a one-size-fits-all rule, but is highly dependent on the local environment and the specific physics of low-mass systems. Understanding which process dominates helps astronomers piece together the early universe, a time when similar tiny galaxies were the primary building blocks of everything we see today. The unusually massive clusters of dwarfs like Fornax are therefore more than just orbital curiosities. They are frozen fossils, each one a clue to the violent mergers or extraordinary birth conditions that shape the smallest galactic structures in the cosmos. While the surviving dwarf galaxies tell one part of the story, the ones that did not survive tell an even more dramatic and revealing tale. Scattered across our galactic halo are the ghosts of past feasts, long, faint rivers of stars that trace the final orbits of dwarf galaxies that ventured too close to the Milky Way's immense gravitational pull. These are tidal streams, the celestial evidence of galactic cannibalism on a grand scale, and they provide us with a powerful tool to perform a kind of cosmic archaeology. The most spectacular and well-studied of these ghostly remnants is the vast ribbon of stars known as the Sagittarius Dwarf Stream. This colossal structure is the shredded corpse of the Sagittarius Dwarf elliptical galaxy, a system that was once one of the Milky Way's most significant satellites. For billions of years, our galaxy has been gravitationally tearing it apart, pulling stars from its body and stretching them into two immense, looping streams that completely encircle the sky like a great cosmic noose. The process of its destruction is a slow-motion gravitational thriller. As the Sagittarius Dwarf orbits the Milky Way, it doesn't follow a simple circular path. Instead, it plunges through the galactic plane on a highly elongated orbit. Each time it makes a close passage, the difference in gravitational pull between the side of the dwarf closest to the Milky Way and the side farthest away creates an immense tidal force. This force, much like the moon's pull on Earth's oceans but on an infinitely grander scale, stretches the dwarf galaxy. Over countless orbits, these repeated gravitational tugs have pulled stars away from the dwarf's main body, ejecting them into leading and trailing streams that now orbit the Milky Way independently, marking the path the dwarf has taken over eons. The small, dense core of the original galaxy still exists, but it is a shadow of its former self, being slowly but inexorably digested by our galaxy, its stars added to the Milky Way's halo one by one. But these streams are far more than just a ghostly memorial. They are the most sensitive gravitational probes we have for mapping the Milky Way's invisible dark matter halo. Think of a tidal stream as a kind of cosmic clock and a measuring tape woven together. The stars within a stream all share a common origin and thus a common velocity. As this long, cohesive filament of stars orbits through the Milky Way's halo, its shape and the precise motions of its stars are exquisitely sensitive to the gravitational landscape it moves through. If the Milky Way's dark matter halo were a perfectly smooth, spherical sphere, the streams would look and behave in one very predictable way. However, detailed maps of the Sagittarius stream reveal something very different. The stream is not a smooth, uniform arc. It shows kinks, gaps, and variations in density. These irregularities are the telltale fingerprints of the dark matter halo's true shape and substructure. By meticulously tracking these stellar rivers, astronomers can reconstruct the gravitational forces that have sculpted them, effectively using the stream as a tool to weigh and shape the invisible component of our own galaxy. The data points strongly toward a halo that is triaxial, shaped somewhat like a gigantic cosmic football or rugby ball, rather than a simple sphere. Furthermore, the fine-scale structure within the streams hints at the presence of dark matter subhalos, smaller, invisible clumps of dark matter that are predicted to orbit within the larger halo. As these subhalos pass through or near a stream, their gravity perturbs it, creating observable kinks and clumps. Finding these disturbances is like seeing the wake of an invisible ship passing through a sea of stars, providing indirect but compelling evidence for the rich substructure predicted by the lambda-cold dark matter model. This makes the study of tidal streams a direct form of galactic paleontology. By reading the patterns in these stellar fossils, we can reconstruct the Milky Way's violent history of accretion, determining not only what it has consumed but also when it happened and from what direction the meal arrived. The Sagittarius stream tells of a massive, ongoing merger. Other, fainter streams, like the one from the Gaia Enceladus galaxy, which merged with the Milky Way some 10 billion years ago, reveal even more ancient chapters of our galaxy's life. Each stream is a chapter in a biography written in starlight, a narrative of growth through collision and consumption. They show us that our seemingly stable Milky Way is not a static island universe, but a dynamic, ever-evolving entity, one whose peaceful spiral disk is surrounded by the shimmering ghosts of its violent past. And just when we thought we had a handle on the role of black holes in dwarf galaxies, another layer of complexity emerges, one that shines with a brilliance we once thought was reserved for the cosmic giants. For a long time, the most luminous and energetic phenomena in the universe, active galactic nuclei, or AN, were considered the exclusive domain of massive galaxies. These are the brilliant beacons powered by supermassive black holes that are actively feeding, pulling vast quantities of gas and dust into an intensely hot accretion disk that can outshine the entire rest of the galaxy. The sheer energy required to sustain such a spectacle seemed to demand the deep gravitational well and abundant fuel reserves of a galaxy like Andromeda or a distant quasar host. The idea that a faint, low-mass dwarf galaxy could harbor such a powerful engine at its core was almost unthinkable. Yet, that is precisely what we are now finding, forcing a dramatic rewrite of the rulebook on black hole activity. The discovery of AGN in dwarf galaxies is like finding a tiny, compact car with the engine of a drag racer. These aren't just the quiet, million-solar, mass black holes we discussed earlier. These are black holes in a state of violent consumption. We detect them through their telltale signatures, bright, flickering X-ray emission that can only come from the innermost, hottest region of an accretion disk, or sometimes through narrow jets of plasma shooting out at near-light speeds. One of the most compelling examples is a dwarf galaxy named Hennies 250, which looks utterly unremarkable in optical light, a simple smudge of ancient stars. But when observed with X-ray telescopes, its center explodes with luminosity, revealing a voracious black hole that is actively stripping matter apart and converting it into raw energy. This isn't a dormant relic, it's a miniature quasar, a powerhouse operating in a galaxy hundreds of times smaller than those we typically associate with such ferocious activity. The significance of this discovery is twofold, and both aspects are revolutionary. First, these active dwarfs provide us with our best local, real-time laboratories for studying the behavior of primordial black hole seeds. In the early universe, before galaxies grew to their immense modern sizes, the first black holes had to start somewhere. The leading theories suggest they began either as the remnants of the first massive stars or from the direct collapse of vast gas clouds. Finding a dwarf galaxy with an active, growing black hole today is like finding a living fossil from that era. We can observe the feeding habits, the jet dynamics, and the energy output of a black hole in a low-mass, gas-rich environment that closely mirrors the conditions of the cosmic dawn. It allows us to watch, up close, the processes that built the first supermassive black holes, giving us a front-row seat to a chapter of cosmic history that was previously only accessible through theoretical models. Second, and perhaps more profoundly, the existence of AGN in dwarf galaxies completely shatters the long-held paradigm of black hole galaxy co-evolution. The established story was one of synchronized growth. A galaxy and its central black hole grow together, their masses closely linked through a series of regulated feedback cycles. The black hole's energy output would heat or expel gas, limiting future star formation and its own growth, creating a tight correlation between the black hole's mass and the properties of its host galaxy's bulge. But dwarf galaxies with active nuclei stand in stark defiance of this neat correlation. Here we have a black hole that is disproportionately active and massive for its tiny host. This suggests that the relationship between a black hole and its galaxy is far more complex and varied than a simple lockstep progression. It implies that black holes can and do grow significantly even in environments that are not conducive to building a large galactic spheroid, and that the feedback mechanisms that regulate this growth might operate very differently in the shallow gravitational potentials of small systems. This opens up a fascinating new frontier in our understanding of galactic evolution. Perhaps these active dwarfs are the exceptions that prove a different rule, that the early universe was a place of chaotic, rapid black hole growth, and that some of these ancient engines have simply persisted in a state of occasional activity within their small hosts, frozen in time. Alternatively, their activity could be triggered by recent minor mergers or the accretion of a small gas cloud, events that are potent enough to stir up the limited fuel in a dwarf but would be mere drops in the bucket for a giant spiral galaxy. Whatever the trigger, the clear message is that black holes can blaze with light across the entire mass spectrum of galaxies. The presence of these brilliant, active hearts in the cosmos's smallest galaxies proves that even the most unassuming cosmic backwaters can become, for a fleeting moment, the sites of the most violent and energetic transformations in the universe. If you try to draw a typical galaxy from memory, you'll likely sketch a majestic spiral, a swirling pinwheel of stars with elegant, symmetrical arms. But step into the world of dwarf galaxies, and that neat cosmic classification system shatters into a spectacular menagerie of forms. Our 20th discovery celebrates this incredible diversity of shapes, a visual feast that reveals how environment and history sculpt these smallest of cosmic islands. Far from being simple, featureless blobs, dwarf galaxies present a stunning array of morphologies, each one a frozen snapshot of a different life story written in starlight. On one end of the spectrum, we have the dwarf spheroidals, the cosmic Zen masters. Think of galaxies like Leo I or Draco orbiting our Milky Way. When viewed through the Hubble Space Telescope, they appear as incredibly smooth, symmetrical, and faint ovals of light. There is no spiral structure, no dust lanes, no bright blue patches of youthful stars. Their populations are overwhelmingly ancient, a uniform sea of old, red suns that have been orbiting in a state of serene equilibrium for billions of years. Their shapes are governed primarily by the gravitational pull of their immense dark matter halos, creating a simple, balanced, and almost featureless equilibrium. They are the galactic equivalent of a still, deep pond, their quiet forms reflecting a long history of quiescence, often imposed by the gravitational bullying of a giant host galaxy that stripped away their gas and halted their internal evolution. In stark contrast, we have the dwarf irregulars, the cosmic abstract artists. Galaxies like the Large Magellanic Cloud or the more distant IC 1613 are glorious, chaotic messes. Imaged in breathtaking detail by the James Webb Space Telescope, they are a riot of structure. There is no defined center or symmetrical form. Instead, you see a scattered collection of brilliant blue star clusters, glowing pink nebulae where new stars are being born, and dark, obscuring dust lanes weaving through the chaos. Their shapes are asymmetric and clumpy, a direct result of their ongoing, turbulent star formation. Each massive star that ignites can blow a bubble in the surrounding gas, and each supernova can trigger further collapse in a nearby cloud, creating a self-propagating, visually chaotic landscape. These are galaxies that are still actively building themselves, their forms not dictated by a smooth gravitational potential, but by the localized, violent feedback of their own stellar children. Between these two extremes lies a whole zoo of intermediate and peculiar types. There are dwarf ellipticals, which are like slightly more massive and concentrated versions of the spheroidals. Then there are the blue compact dwarfs, which we've met before, appearing as small, roundish balls that are nonetheless blazing with the intense blue light of a galaxy-wide starburst. And we cannot forget the ultra-diffuse galaxies, those enigmatic cosmic ghosts that have the sizes of giants but the stellar contents of dwarfs, appearing as vast, wispy, and almost transparent smudges against the dark sky. The Hubble and Webb images of these various types are not just pretty pictures. They are data-rich maps that allow astronomers to classify and, more importantly, to understand the physical processes at work. So, what creates such a dramatic divergence in form? The answer lies in a delicate cosmic tug of war between three fundamental forces: mass, environment, and star formation history. A dwarf galaxy's mass, particularly the mass of its dark matter halo, sets the stage. A more massive halo provides a deeper gravitational well, which makes it harder for supernova explosions to blow out all the gas, allowing for more sustained star formation and potentially a more structured evolution. Environment is perhaps the most decisive sculptor. A dwarf irregular galaxy floating in the peaceful isolation of the cosmic field can hold onto its gas for billions of years, perpetually refreshing its star-forming material and maintaining its messy, irregular appearance. But if that same galaxy falls into the orbit of a giant like the Milky Way, its fate changes dramatically. The giant's gravitational tides strip away its gas and harass its stars, rapidly shutting down star formation. Within a surprisingly short cosmic time, the vibrant, irregular dwarf is transformed into a quiet, smooth, spheroidal satellite, its chaotic youth erased, its form simplified into a placid, red and dead relic. Finally, the star formation history itself is written directly into a dwarf galaxy's morphology. A galaxy that formed all its stars in a single, initial burst billions of years ago has had ample time for the orbits of its stars to randomize, settling into the smooth, featureless shape of a spheroidal. There is no new star formation to create bright, blue knots or to stir up the interstellar medium. Conversely, a galaxy experiencing continuous or bursty star formation will always look irregular and clumpy. The brilliant but short-lived massive stars are constantly illuminating new regions and churning the galactic gas, preventing the system from ever reaching a state of relaxed, symmetrical equilibrium. The glorious, untamed shape of a dwarf irregular is therefore the signature of a galaxy that is still alive, still breathing, and still giving birth to new suns, a vibrant testament to the ongoing, dynamic creativity of the universe, even on its smallest scales. Tucked away in the constellation of Leo, far from the brilliant lights of major galaxies, floats one of the most enigmatic structures ever discovered, a colossal, ethereal ring of primordial gas known as the Leo ring. This isn't a ring of stars or the debris from a collision. It is a vast, rotating loop of neutral hydrogen, so immense it could easily envelop our entire Milky Way galaxy. For decades after its discovery, it was considered a celestial oddity, a ghostly afterthought in the grand scheme. But recent observations have transformed this ring from a curiosity into a revolutionary possibility. It may be a dark, dwarf galaxy in its raw, unprocessed form, a pristine cloud of gas that has somehow existed for billions of years without ever igniting the fires of star formation, a living fossil from the universe's youth. The sheer scale and nature of the Leo ring are what make it so extraordinary. It orbits in the gravitational domain of two large galaxies, M105 and NGC 3384, and contains enough hydrogen gas to create an entire dwarf galaxy's worth of stars, perhaps even billions of them. Yet, when we look at it with optical telescopes, there is almost nothing there, just a faint, diffuse veil against the darkness. The gas is cold, pristine, and remarkably poor in heavy elements, indicating it has not been processed through the life and death cycles of previous stellar generations. This suggests the ring is a relic, a leftover building block from the era of galaxy formation that has, against all odds, avoided the fate of its contemporaries. It's like finding a vast, untouched quarry of raw marble next to a city of finished sculptures. It represents the potential for creation that was never realized. So, what cosmic conditions could have prevented this enormous reservoir of gas from collapsing to form stars? The leading theories point to a delicate and fascinating interplay of forces. One compelling idea is that the ring exists in a state of gravitational peace. Its immense size means its internal density is incredibly low, and the gas may be too diffuse for the initial, crucial seeds of collapse to take hold. Without dense enough knots of gas, gravity cannot overcome the internal pressure and thermal support to begin the process of star birth. It's stuck in a cosmic limbo, too spread out to ignite. Another crucial factor is the lack of a triggering event. In most galaxies, star formation is jump-started by external shocks, the gravitational squeeze from a nearby galaxy's passage or the collision of two gas clouds. The Leo ring, however, appears to be dynamically tranquil, floating in its gentle orbit without experiencing the violent disturbances that typically compress gas and light the stellar fuse. This pristine nature makes the Leo ring an invaluable time capsule. It offers us a direct look at the primordial material from which all galaxies were built. By studying its composition and dynamics, astronomers can measure the properties of the intergalactic medium as it was billions of years ago, before stars polluted it with heavier elements. It acts as a control sample, showing us what the universe's raw ingredients were like before the complex cooking process of galactic evolution began. Furthermore, its very existence provides a potential solution to part of the missing dwarf problem we explored earlier. The universe's simulations predict thousands of small dark matter halos. Perhaps a significant fraction of them are just like the Leo ring halos that successfully gathered gas but for a variety of reasons never crossed the threshold to become luminous galaxies. They are the cosmic dark matter, the silent majority of galactic building blocks that never announced their presence with starlight. The future of the Leo ring is as intriguing as its past. Its current state of quietude may not last forever. The gravitational influence of its two massive host galaxies could eventually destabilize it, or a future close encounter might send shockwaves through the gas, finally triggering a belated but spectacular burst of star formation. It might be on the cusp of a delayed awakening, a dormant giant about to be stirred. By continuing to observe this primordial cloud with the most sensitive radio and optical telescopes, we are essentially watching a paused movie of galactic birth, a process frozen in its very first act. The Leo ring challenges our definitions and reminds us that a galaxy is not defined solely by its stars, but also by its potential. And in this vast, silent ring, the potential for an entire galactic future is still waiting in the wings. Imagine you could read the biography of a single star written in the language of its atoms, a permanent record of where it was born and the environment that nurtured it. This isn't science fiction, it's the powerful technique of chemical tagging, and when applied to the countless stars in the halo of our Milky Way, it reveals a dramatic history of galactic cannibalism on a colossal scale. The halo is the vast spherical cloud of ancient stars that envelops our familiar spiral disk, and for a long time its origins were murky. Did these stars form in place as the primordial Milky Way itself coalesced, or did they arrive from elsewhere? The answer, written in starlight, points unequivocally to a violent past where our galaxy grew by consuming its smaller neighbors, with the dwarf galaxies we see today acting as living proxies for the building blocks of our own home. The process of chemical tagging works because a star's atmosphere preserves the elemental composition of the gas cloud from which it formed. Elements like iron, magnesium, oxygen, and europium are forged in different types of supernova and at different rates. Massive stars explode quickly, seeding space with alpha elements like oxygen and magnesium. Slurming white dwarf binaries take much longer to detonate as type Ia supernova, flooding their surroundings with iron. In a large, well-mixed galaxy like the Milky Way's disk, this cycle is continuous, resulting in a predictable and consistent relationship between these elements across a vast population of stars. But when astronomers turned their spectrographs to the halo stars, they found a stunningly different pattern. The chemical signatures were all over the map. Some stars had very high ratios of alpha elements to iron, while others had much lower ratios with no smooth progression in between. This lack of a single, coherent chemical history was the first major clue that these stars were not all born in the same cosmic cradle. The real breakthrough came when scientists compared these chaotic halo signatures to the chemical fingerprints of stars in nearby dwarf spheroidal galaxies like Sculptor and Fornax. The match was uncanny. The distinct low alpha to iron ratios found in many halo stars were virtually identical to the patterns seen in dwarfs. This is the cosmic equivalent of finding a specific, rare dialect spoken in an isolated village, and then discovering that same unique dialect scattered among individuals in a massive metropolis. It's a powerful indicator of a shared origin. The inescapable conclusion is that a vast number of the stars in our galactic halo did not form here. Instead, they are immigrants, the captured stellar populations of dwarf galaxies that were shredded and assimilated by the Milky Way's gravity over billions of years. This evidence transforms our understanding of the halo from a simple, primordial structure into a dynamic archaeological site, a celestial graveyard of consumed galaxies. Every star with a chemical signature matching a dwarf galaxy is a relic of a past merger event. By cataloging these chemical fossils, astronomers can begin to piece together the family tree of the Milky Way, identifying not just that accretion happened, but how many different dwarf progenitors contributed to the mix. Current estimates are staggering, suggesting that the halo we see today might be the assembled remnant of hundreds of distinct dwarf galaxies, with their stars now thoroughly mixed into a single, swirling cloud. The few dozen dwarf satellites we see orbiting us today are merely the survivors, the ones that haven't been fully devoured yet, offering us a living glimpse into the building blocks that constructed our galactic home. This narrative of hierarchical growth is powerfully confirmed by the ghostly tidal streams we discussed earlier, like the one from the Sagittarius dwarf. These streams are the direct visual evidence of ongoing accretion, showing a dwarf galaxy in the process of being unraveled. Chemical tagging provides the complementary forensic evidence for the mergers that have long since concluded. The stars from those fully digested dwarfs are now completely dispersed throughout the halo, their orbital clues erased by time, but their chemical DNA remains an immutable record of their extragalactic origin. Together, the streams and the chemical tags paint a complete picture. The Milky Way is not a static island universe, but a dynamic, ever-evolving entity that has built its immense halo star by star, galaxy by galaxy, in a continuous cosmic feast. Yet another layer of mystery within these tiny galaxies has emerged from a force that is literally invisible to our telescopes, yet its effects can be mapped across the void. We now come to the surprising detection of ordered magnetic fields weaving through dwarf irregular galaxies. Magnetic fields are a fundamental part of our cosmic environment, and in large spiral galaxies like our own, they are incredibly powerful, threading through the spiral arms and helping to shape the birth of stars. But for the longest time, astronomers assumed that such well-ordered, large-scale magnetic fields were a luxury reserved for these grander cosmic systems. The reasoning was based on a process known as the dynamo effect. Think of a galactic dynamo as a kind of self-sustaining cosmic generator. It requires a few key ingredients to work. A galaxy needs to be rotating fairly rapidly, and it needs to have gone through multiple cycles of star formation and supernova explosions. These violent stellar deaths stir and churn the interstellar gas, twisting and amplifying weak, primordial magnetic fields into the strong, organized ones we can detect. Dwarf irregular galaxies, with their slow rotation and often simple, single-burst star formation histories, were thought to be missing these essential ingredients. They were the cosmic equivalents of small towns without a power plant, expected to be dark, magnetically speaking. That assumption was turned on its head when radio astronomers pointed their most sensitive instruments at dwarf irregulars like the Large Magellanic Cloud and a more distant galaxy known as IC-10. By studying the polarization of radio waves emitted by these galaxies, they could trace the orientation of magnetic field lines. The expectation was to find only a weak, chaotic jumble of magnetism, a fossil field left over from the galaxy's formation. Instead, they discovered something astonishing. In several of these small systems, the magnetic field showed a surprising degree of order, stretching across thousands of light years in coherent patterns. It was like finding a perfectly organized power grid in a village that was only supposed to have a few scattered, flickering candles. This detection immediately raised a profound question. If these small galaxies lacked the powerful dynamos of their larger cousins, how did they build such structured magnetic fields? This puzzle has led scientists to explore some fascinating and unconventional possibilities. One compelling theory is that we are witnessing the direct legacy of the very first magnetic fields in the universe. Perhaps these ordered fields in dwarfs are not internally generated at all, but are primordial relics. In this scenario, these magnetic fields were woven into the fabric of space-time during the universe's earliest moments, and they were subsequently stretched and amplified as the galaxies themselves formed from the expanding cosmic web. Dwarf irregulars, being relatively simple and undisturbed systems, could have preserved these ancient fields in a more pristine state, like a time capsule holding onto the universe's original magnetic blueprint. Their slow, tranquil evolution might have prevented the chaotic turbulence that would otherwise scramble these delicate structures in larger galaxies. Another, more dynamic explanation involves a process called a small-scale dynamo. Even if a dwarf galaxy doesn't rotate quickly as a whole, its interior can be a hotbed of localized turbulence. The powerful stellar winds from massive stars and the shock waves from frequent supernova in a star-forming dwarf can create a violent, churning mess on smaller scales. This turbulence itself could act as a potent, if less orderly, dynamo. It might not generate a single, galaxy-wide magnetic field like the Milky Way's, but it could amplify random seed fields into strong, localized magnetic structures that, when viewed from a distance, appear as a coherent large-scale field. It's a bottom-up approach to building cosmic magnetism, where the collective chaos of countless stellar explosions creates an emergent order. The presence of these fields is far from just a cosmic curiosity. It has real, tangible consequences for the life cycle of the galaxy itself. Magnetic fields exert pressure within a vast, collapsing cloud of gas that is destined to form new stars. Magnetic pressure can act as a support mechanism, fighting back against the inward pull of gravity. In a giant spiral galaxy, this can simply slow down the star formation process, making it more efficient. But in a dwarf galaxy with a much weaker gravitational pull, a strong magnetic field could be a decisive factor. It might be powerful enough to completely prevent some gas clouds from collapsing, effectively putting a brake on star formation and helping to explain why some dwarfs have such low star formation rates despite having ample gas reserves. Conversely, magnetic fields can also channel flows of gas, guiding material along their lines of force and actually helping to create the dense, filamentary structures within which stars are born. So, the same magnetic field can play a dual role, both a suppressor and a midwife of stellar birth. Its ultimate effect depending on the delicate balance between magnetic, thermal, and gravitational pressures within the fragile ecosystem of a dwarf galaxy. This unexpected magnetic personality in the smallest galaxies reveals that the forces shaping cosmic evolution are even more complex and interconnected than we ever imagined, proving that even the faintest galactic systems are governed by a rich and dynamic physical tapestry. This brings us to a frontier where the cosmic and the subatomic collide, a place where the faintest galaxies in the sky become our most powerful microscopes. For decades, the hunt for dark matter has followed two main paths. One is the direct approach, with sensitive detectors buried deep underground, waiting for the elusive ping of a dark matter particle bumping into an ordinary atom. The other is to create it, slamming particles together in colossal accelerators like the Large Hadron Collider in hopes of producing it from pure energy. But there is a third, profoundly elegant path, indirect detection. And for this method, dwarf spheroidal galaxies are, quite simply, the perfect hunting ground. They offer a pristine, quiet environment to listen for the faint, final whispers of dark matter particles meeting their end. The logic behind this is as powerful as it is straightforward. Many of the leading theoretical candidates for dark matter, particles with names like WIMP, weakly interacting massive particles, or actions, are thought to be their own antimatter counterparts. This means that when two of them collide, they could annihilate one another, converting their entire mass directly into energy according to Einstein's famous equation, E equals mc². This energy would manifest as a cascade of standard model particles, which would then rapidly decay into a predictable shower of gamma-ray photons, the most energetic form of light in the universe. Alternatively, if the dark matter particle is unstable, it might simply decay over astronomical timescales, also producing a faint but steady glow of gamma rays. In either case, the key is to find a place in the universe that is absolutely teeming with dark matter, but has very little of the messy astrophysical background that could mimic this signal. That place is a dwarf spheroidal galaxy. Consider the properties that make these dwarfs so exceptional for this task. First, and most importantly, is their incredible mass-to-light ratio. As we've seen, galaxies like Draco or Segue 1 are essentially colossal balls of dark matter with a few stars sprinkled in. This means the density of dark matter particles in their cores is astronomically high, dramatically increasing the probability that any two particles will collide and annihilate. The rate of this annihilation depends on the density squared, so doubling the density doesn't just double the signal, it quadruples it. The ultra-dense cores of these dwarfs act as powerful natural particle accelerators and concentrators, far exceeding anything we could ever build on Earth. Second, and just as crucially, these galaxies are incredibly clean. They are largely devoid of the other high-energy phenomena that produce gamma rays and could create confusing background noise. In a massive spiral galaxy like our own, the gamma-ray sky is a cacophony. You have pulsars spinning like cosmic lighthouses, supernova remnants accelerating particles to near light speed, and vast clouds of gas being lit up by cosmic rays. Trying to pick out a faint, uniform dark matter signal from that stellar racket is like trying to hear a whisper in a roaring rock concert. But in a dwarf spheroidal, the concert is almost entirely silent. There is very little gas, no recent supernova, and typically no pulsars or other energetic objects. If you see a steady, diffuse glow of gamma rays emanating from one of these dark matter dominions, it is very difficult to explain by any conventional astrophysical process. It would be the smoking gun that physicists have been searching for. For over a decade, the premier instrument in this hunt has been the Fermi Gamma-Ray Space Telescope, which has been scanning the entire sky for these high-energy photons. Scientists using Fermi's data have performed meticulous analyses on dozens of the Milky Way's dwarf spheroidal satellites, stacking the data from many galaxies to enhance the sensitivity of the search. The strategy is one of statistics and patience. While no single dwarf has yet produced an unambiguous standalone detection, the combined null result from all of them has been profoundly informative. It has allowed researchers to place the most stringent limits to date on the properties of dark matter particles. We can now say with great confidence that if the dark matter is a WIMP, it cannot be lighter than a certain mass or interact more strongly than a specific cross-section, because if it did, Fermi would have seen its gamma-ray signature shining from these dark matter fortresses. This null result, while not the dramatic discovery we might hope for, is actually a crucial form of progress. It has systematically closed off vast territories of theoretical possibility, forcing particle physicists to refine their models and look to other candidates or different mass ranges. The hunt continues to evolve, with astronomers now also searching for other potential signals, such as neutrinos or anomalous radio waves that could be produced by actions interacting with magnetic fields. The dwarf galaxies, in their quiet perseverance, continue to act as our silent partners in this grand investigation. They are the ultimate natural laboratories, their existence and properties constraining the fundamental laws of particle physics from light years away. Every new, faint dwarf discovered and added to the census improves our statistical power, sharpening our cosmic microscope and bringing us one step closer to finally identifying the mysterious substance that shapes the cosmos. And so we reach our final and perhaps most profound discovery, one that doesn't just look at dwarf galaxies as they are today, but uses the most powerful time machine ever built to witness their birth at the dawn of time. The James Webb Space Telescope, with its infrared eyes peeled back to the first few 100 million years after the Big Bang, is now showing us the universe's very first galaxies. And in a stunning revelation that is turning cosmology on its head, it appears the infant cosmos was absolutely teeming with small, red, and incredibly active dwarf galaxies, objects that are challenging our most fundamental scripts for how the cosmic story began. For years, our best models of the early universe predicted a relatively slow and gradual start to galaxy formation. The first structures to ignite were thought to be faint and few, gradually merging and growing over billions of years into the majestic spirals we see today. But the universe, it seems, had other plans. The very first deep field images from Webb revealed a startling abundance of small, crimson smudges of light, each one a nascent galaxy seen just as it was emerging from the cosmic dark ages. These aren't the colossal giants we might have expected. They are the primordial ancestors of today's dwarf galaxies, and they are far more numerous, brighter, and more evolved than anyone anticipated. They appear to have formed stars at a ferocious rate, lighting up far earlier and more brilliantly than our simulations said was possible. It's as if we opened a history textbook expecting to find a few simple cave drawings, only to discover entire, bustling cities already in full swing on the very first pages. This unexpected brightness and early maturity pose a thrilling challenge to our understanding of the early cosmos. How could such small, young galaxies assemble their stars so quickly? One leading theory points to the nature of the first stars themselves. These weren't the well-behaved, long-lived stars like our Sun. The earliest stellar generations, known as population 3 stars, were behemoths monumentally massive, intensely hot, and blazingly luminous. They lived fast and died young in cataclysmic explosions that would have rapidly enriched their tiny host galaxies with heavy elements. A dwarf galaxy forming even a handful of these stellar titans would shine with an incredible brilliance in its youth, explaining the surprising luminosity Webb is detecting from such small, distant systems. Their fierce ultraviolet light would have been exactly the kind needed to help blow away the universe's primordial fog during the epoch of reionization, casting these tiny dwarfs in the role of the universe's primary light bringers. The sheer number of these early dwarfs is equally transformative. Webb's deep surveys suggest that the early universe was a cosmos of small things, a sprawling metropolis of nascent dwarf galaxies. This vast population provides a compelling solution to a long-standing mystery. How did the massive galaxies we see today get so big, so fast? The answer now seems to be that they were built from the bottom up by the relentless merging of countless tiny dwarfs. The universe didn't start with a few grand designs. It began with a cosmic sea of tiny bricks, and galaxy formation was a process of continuous, chaotic assembly. Every giant spiral like our Milky Way is likely the assembled remnant of thousands of these primordial dwarfs, their identities long since lost in the grand merger that built our home. These groundbreaking observations are forcing a comprehensive rewrite of our early galaxy formation narratives. cosmologists are now scrambling to adjust their models, incorporating more efficient modes of star formation, different properties for dark matter, or even new physics for how gas cooled and collapsed in the pristine early universe. The quiet, gradual cosmic dawn we once imagined is being replaced by a vision of a vibrant, dynamic, and surprisingly precocious infancy, where dwarf galaxies were the undisputed protagonists. With every new deep field image, Webb is not just showing us the past, it is actively refining our understanding of the fundamental processes that gave rise to all structure in the cosmos. These faint, red smudges on the edge of observable reality are the humble beginnings of everything we know, and they are telling us that the story of our universe started with a bang far louder and more brilliant than we ever dreamed. What a wild journey it has been, from the ghostly vastness of ultra-diffuse galaxies to the brilliant firestorms of blue compact dwarfs, from the invisible, crushing dominance of dark matter in one galaxy to its perplexing absence in another. We have ventured through a cosmos that is far stranger and more wonderful than we ever imagined. We have seen how these tiny galactic realms challenge our most fundamental assumptions at every turn. They defy the predicted hierarchy of the missing dwarf problem. They assemble in impossibly thin, rotating planes that our best simulations cannot replicate, and they host ancient, pristine stars alongside supermassive black holes that have no business being there. They are cosmic fossils, celestial rebels, and galactic building blocks all at once. Each of these 25 discoveries reveals that dwarf galaxies are not the simple, quiet backwaters of the universe. They are, in fact, the primary arenas where the great dramas of modern cosmology are playing out, forcing us to question the very nature of dark matter, rewrite the story of galaxy evolution, and reconsider our place in a cosmos where even the faintest lights can illuminate the deepest truths. As we stand at this frontier of knowledge, the most thrilling part is knowing that this is only the beginning. The revolution in our understanding of these miniature powerhouses is about to accelerate at a breathtaking pace. In the coming years, the Vera C. Rubin Observatory, with its gigantic camera that will scan the entire southern sky every few nights, is poised to completely transform the field. It is expected to discover not dozens, not hundreds, but millions of new dwarf galaxies, painting a picture of the local universe with a richness and detail we can barely conceive of today. We will find dwarfs fainter than any we have ever seen, dwarfs in stranger environments, and dwarfs with properties that will undoubtedly challenge our current catalogue of cosmic anomalies. This flood of new data, combined with the profound insights from the James Webb Space Telescope peering into the ancient universe, will provide the statistical power to finally answer some of our most pressing questions, while simultaneously and certainly revealing entirely new mysteries we haven't even thought to ask yet. So, as we conclude this deep dive into the smallest and most enigmatic corners of the cosmos, we turn the question over to you. Which of these 25 strange discoveries reshaped your own view of the universe the most? Was it the realization that most of the cosmos is made of an invisible substance that reveals itself most clearly in the faintest galaxies? Or was it the bewildering existence of a galaxy the size of the Milky Way built from little more than cosmic mist? Perhaps it was the coordinated dance of satellite galaxies in vast, spinning planes that defies our best models. Let us know in the comments below which finding baffled you the most. If you enjoyed this journey to the frontiers of cosmic mystery, make sure to subscribe and hit the notification bell, because we have many more deep dives into the universe's greatest puzzles coming your way. The cosmos is whispering its secrets, and together we can